Okay, let's develop the derivative definition. You'll want to turn to that page in your notes. You'll want to draw the set of axes that I have here. And we're going to draw the generic function. You don't want to be too careful on this. We're just going to give it a little bit of a swoosh feeling. Okay, and that's our function f of x. Again, please don't lose sight of the big picture. The big picture is we're trying to figure out what the slope is of the curve when it's not just a linear, but it's a curvy function. We want to find the instant slope or instantaneous slope or instantaneous rate of change. So I'm going to put a x equals a here. This is where it's all going to happen. I want to figure out what is the slope of this function f of x at this point, x equals a. The corresponding y value for that a is going to be clearly f of a, and so that's going to be some real number f of a. From the introduction, we said we can understand an instant slope if we knew we had a tangent to the curve. So I'm going to draw that tangent to the curve. Oh, I kind of like it. Normally I foul it up, but I'm happy that I didn't. And this line that I have drawn is called a tangent line, and this tangent line touches the curve at that one and only one point. And we discussed in the introduction that if I could come up with the slope of that tangent line, well, then I would have the slope of the function at the particular point. I think I'm going to label this as the tangent line. And when all is said and done, all this theory is going to basically give us an equation for the slope of this tangent line, and that'll be the final result. But before we do that, I'm going to pick a different color. Let's go with more of a pink color. I'm going to draw a line that is not a tangent line. That line is going to also go through this point here, but then it's going to go through a point up here. Let's highlight it. Now, carefully, I'm going to draw a line. It's not a tangent line because it cuts through the curve. And I'm trying my best to draw this carefully. Okay. Please be convinced that that is straight. Although it doesn't appear to be perfectly straight, I think you get the idea. This line that I drew that cuts through is not a tangent. A tangent does not cut through. In this case, this is called a secant line. That's not ultimately what we want. I don't want the slope of a secant line. I want the slope of a tangent line. But to develop this definition, we are going to talk about what is the slope of that secant line. Now, where does that cross? Well, it can cross anywhere. This is supposed to be a generic drawing. So I'm going to label this x to represent any value of x. I literally could have drawn it to the left. Now, a is fixed. This value doesn't change. That's our starting point. But this x could really have been drawn anywhere. Now, a little bit of rise over run, a little bit of algebra is going to tell us what the slope of the secant line is. And so if I do change in y over change in x, let's go ahead and label this corresponding y value to be f at varying x. And so we would define the slope of the pink secant line to be change in y over change in x. F of x minus f of a all over x minus a, and that's just change in y over change in x. That slope does not give us the instantaneous rate of change. I'll say it a million times, the instantaneous rate of change is the slope of the tangent. So if this red or pink line slope does not give us the instantaneous rate of change, what does it give us? And unfortunately, I'm just going to have to tell you, you may know it already, it gives us an average rate of change. So the secant line is associated with average rate of change, while the tangent line is associated with an instantaneous rate of change. And that brings us to the very thing we want to find. This is it. This is what we're trying to find. We're trying to find m. So m is going to be, m of the tangent line is going to be related to m of the secant line. And how will I relate them? What vehicle? Now we're trying to word this in a way you might see it. I want to take this pink line that I have, and I want to push it down. I want to shimmy. In fact, I'm basically shimmying this point. If I shimmy that point, then a secant line might go to this point, might go to this point, might go to this. And if I shimmy it, the pink eventually becomes the blue. So the question that I want to ask is, what vehicle shimmies or pushes pink to blue? We don't change the A value. That point here will stay. I want to shimmy, though, the curve itself, kind of revolving about that A. And I hope maybe you're thinking it. The idea is that this X has to get close to A. It has to get instantaneously close. It has to get closer and closer and closer. And so the vehicle that does that is a limit. That was the last unit. So this is going to be this very specific limit. It's the limit as X gets close and close and close, or approaches A, of this special ratio. So it's the limit as X approaches A of f of X minus f of A all over X minus this special ratio, the difference quotient. So slope of the pink is the difference quotient, and the slope of the blue is the limit as X approaches A of the difference quotient. And this here, my friends, is a very, very, very important equation. It gives us a derivative at X equals A. Some of you might have seen formulas for derivatives, but seen it in a slightly different way. So I want to address that way now too. In fact, what you see here is called an alternate approach to something you may have already seen. So we're going to approach this a little differently. We have our A and our X. Instead of talking about the random point X, let's talk about the difference between that X and the value of A. What would we call that difference? Hopefully you're thinking delta X, or the change in X. And you are absolutely correct. Now, our textbook uses an H. Please note that H is simply another symbol for delta X. And so now this point X can be related to the original point A. Instead of saying this is the point X equals X, we can say this is the point X equals the A plus the delta X, or A plus H. So we have this value here now, which is A plus H. And the corresponding Y value, of course, is going to be f of A plus H. Utilizing that, we're going to come down to our secant, and we're just going to rewrite the difference quotient using that methodology. Instead of f of X, we're going to say f of A plus H minus f of A all over. Now this is kind of interesting. The denominator is going to be A plus H. That replaces the X minus the A, and you can see that that simplifies to have a denominator of simply H, or again, simply delta X in the denominator. And that one might start to look more familiar with something that you've done in a previous course. So we're going to come down here now for the tangent, and we're going to write a limit statement. So this is going to be the limit. Now this is really important, so I'm going to wait on something here. We have the difference quotient, f of A plus H minus f of A all over H. But what is the limit now? What, instead of saying X approaches A, hopefully you're thinking the limit as H goes to 0, or the limit as delta X collapses. And there we have it. I can't emphasize enough how important these definitions are. These are the definitions for the derivative at X equals A. They give us a number value, provided that they exist. They give us a number value that tells us the instant slope of the function. So if I were able to come up with that number, let's say the number was 7, well, that would be the instantaneous slope at X equals A, 7. The form here that represents the secant with the A plus H and represents the slope of the tangent with the A plus H, that is considered the standard. The other one that we actually did first, the one that uses f of X and f of A, those are considered the alternate, and we're going to summarize that below. And so here, the average rate of change, the standard definition is going to be what we wrote above, f of a plus h minus f of a all over h, the difference quotient. And the bottom version of this, it's going to be f of the value x minus the f of the value a all over x minus a. These are both change in y over change in x. So now on the interval a to b, which would be a fixed interval, the average rate of change would be f of b minus f of a all over the b minus a. I simply want you to know that, though, as the change in y over the change in x. That's what it's referring to. And now for the instantaneous rate of change, the very thing that we're trying to learn in the unit, the slope, the derivative at x equals a, is going to be defined as follows. I'm going to introduce a little bit of notation here. I'm going to say f prime of a. This is a fancy way of saying the derivative of the function at x equals a. The prime represents notation to say derivative or slope. So one would read this as, what is the slope of the function f at the point x equals a? So this was developed by the mathematician Lagrange using this prime notation, but we're going to use this so often that you'll get comfortable with it, I feel confident, pretty quickly. And the standard definition for the derivative or the slope at x equals a is this limit as h approaches 0 of f of a plus h minus f of a all over h. You might be thinking and say to yourself, I kind of remember this formula before. I kind of remember saying the limit as h goes to 0 of f of x plus h minus f of x over h. And if you're thinking that, I need you to kind of unthink that for a moment, because that does represent a derivative, but that represents a derivative function. And right now, we're not talking about the derivative function. We're talking about the derivative at a particular value. So the answer would be a number, a real number, provided that it exists. The alternate, we're still going to use f prime of a, and the alternate definition would say the limit as x approaches a of f of x minus f of a all over x minus a. Now, of course, these are answers or numbers provided it exists.